Welcome back to Mechanics and Control of Robotic Manipulator. I hope you would have enjoyed in the last lecture where the simulations all come. So it is actually giving little more intuition. So I hope you are able to even extract the MATLAB code from the handout and you would have tried your own. So now in this particular lecture we are continuing that part where we left. So we left that actually we have seen what is cubic polynomial, how to generate the cubic polynomial in MATLAB even with wire point. So this particular lecture we are going to see how to generate a higher order polynomial with a MATLAB function and similarly cycloidal and straight line interpolation with parabolic blend. So in that case we will actually try to see these are the 3 points. So where the fifth order polynomial we call quintic, so which is a Latin word. So Latin word quintic means fifth. So similarly the cubic means third. So this is the way we also try to see. So in that sense we will actually see what equation we have derived in the regular lecture. So these are the equations which we have derived in the regular lecture. So this can be portrayed with the initial and final condition. You can see here the acceleration also controllable. So the initial acceleration and final acceleration if you equate, so there would be 6 unknowns and 6 equation we can generate. Those 6 equation and 6 unknown we can write it in a matrix and vector form. So where a naught to a phi are unknown, so x naught to x double dot of tf are known, and this is actually coefficient matrix where inside all the terms are actually known to us. So in that sense we can take this as a and this is x and this is b. So we can take x is a inverse of b. So the same principle we will try to do it in MATLAB. So for that we are taking the same code. So we are modifying certain parameter. So you can see this is what we have taken for the cubic polynomial. We have taken as a tf as 5 second, and it is actually varying as a span where t is starting from 0 to tf, and the initial condition and final, you can say initial position and final position, initial velocity and final velocity are known in cubic polynomial. But in this case, so even the acceleration also known. So here I have written as dd dot, or you can say d dot, so which means double dot. So these are also given. So based on this we can actually rewrite the coefficient matrix. Earlier case it was 4 cross 4. So now this is 6 cross 6. So we have written this. So now based on this, so we can actually find the coefficients. So where the B matrix actually B vector can be given, then the trajectory coefficient can be calculated. So then this is all actually standard protocol. So you can see this is the you can say position, this is the velocity and acceleration, and we can use the same MATLAB function how we have written the plotting function. So the same thing we can use it. So now in order to understand this, so we are actually going to the MATLAB window, and I am actually trying to show that. So I think the fifth order polynomial. Okay. Okay, so this is the fifth order polynomial. So where you can see these are all actually what we have written in the, you can say, handout, and this is the A matrix we have written in the same you can say handout. So we have not changed, and B vector we have actually assumed to be known. These are all initial and final conditions including position, velocity and acceleration all known. So we have actually calculated the coefficients. So then we have actually generated the trajectory, and we are actually trying to plot. So now we will take the same case, okay. So where it is actually start from 0 and it end with 5 with the 5 second. So we can actually try to see so how it is actually going. It is much more smooth. You can see the acceleration earlier case it was actually you can see non-zero initial and final acceleration, but in this case I have given 0 0 initial and final accelerations. So you can see it is a very smooth curve. So even you want to actually make it much more interesting fact. For example, I said that this is, so minus 1 is the initial velocity and final velocity is 1, which we have tried in the cubic polynomial. The same thing I am actually trying to show here. So you can see it start, still the acceleration profile is actually smooth. It's more close to a sinusoidal curve. It is not strictly sinusoidal, it is a smooth. It's very close to sinusoidal. So that is what the sinusoidal anyhow we are going to see in cycloidal. So this is what the curve. Since it is actually non-zero initial velocity, that's why it is going the way. So that too it is starting from what you call minus 1 meter per second. So that's why it is actually like going down and go. However, you can see like the maximum velocity is coming the same midpoint, which is 2.5 second. So that particular point you can see the acceleration also like 0. Okay. So even you want to see little more you can say inside, I just put it initial and final velocity is 1. So you may expect that it would become as a constant. It is not. It is again like a go as a smooth. So we can actually like try to see that. Okay. So you can see like it is starting from 1 and actually like from 1 to 1 it is added. Okay. So because we assume that initial velocity is actually like 0. So that way actually like it is actually like making it addition. Okay. So now in that case we can actually like see this aspect how it is actually like going. So this is added from the initial. So that way we can actually like see. So now I am actually like putting this as actually like a 0. So you can actually like feel it, that is ending with 1. Okay. So now this I am actually like putting it 0 and this is I am putting it 2 and this is I am putting it actually like 3. You can see that variation, whatever variation you can actually like do it, these all we can do it. Now you can see it is actually like much different, right? So these all actually like we can actually like try to see and get it done. Okay. So here I did not make it. Yeah. So now we can actually like see even if it is 0 final velocity, it is actually like end, right? So now I hope how the fifth order polynomial is working. So and what are the parameter you can vary. So the one is actually the time span, which is actually like how what and how you can actually like make the acceleration, that is also like consideration. For example, now the final acceleration is supposed to end with 0.1. So you can see like it is actually like end with 0.1. So in order to give little more you can say explicitly visible, so I am putting it as actually like 1 meter per second square. So you can actually like see it, right? It is actually like ending. So these all can be done with you can say fifth order polynomial, and even you can give initial acceleration is actually like minus 1 meter per second squared, which is actually starting from different profile, it end with a force which is in a negative direction. You can actually like see, right? So all those things are actually like coming into picture. However, the profile is not changing. Only thing, the velocity profile and the acceleration profile is changing. So here in the sense it is not changing, in the sense starting and ending point is not changing, it is actually like following the smoothness. So that is what I mean to say it is not changing. Okay. So now we will actually like go back to the slide. So where we will be seeing about what is cycloidal motion. So the cycloidal motion is actually like we can rewrite in terms of position, velocity and acceleration in this form. I don't want to cancel this 2 pi everywhere, because if I cancel then I have to bring it here 1 by 2 pi, then that would be all the time residue. So that's why I have written in this general form. So where while we are calculating we assume that t0 is actually like 0. So in that case, so how the MATLAB function will look like, the initial stage everything is same, in the sense these all actually like same. So only thing here x0 and xf are the input, because the cycloidal we assume that it is starting from rest and ending with again it rest, in the sense it is going to be stop. So no further motion. So it is actually starting from rest and going to end. That is what the segment says. So in that sense we can actually like generate the position, velocity and acceleration in this form. So now this is the cycloidal profile, and the same thing we can use as for plotting and all. I am not showing the plotting here. So now we will actually like open the file which we make it. So cycloidal, I hope. So now you can see this is the command which we have given in the you can say handout, and this is the trajectory generation, and this plotting we have used earlier, the same thing I have tried. So now the same case we are trying. So it take 5 seconds to reach 0 to 5 in a smoother sense. So we can actually like try to see by running this. So you can actually like see it. So it is actually like very smooth, but here we don't have any control over initial and final velocity, initial and final acceleration. However, it start from 0 and end also at 0. In that case, acceleration and velocity all start from 0 and end at also 0. In that sense, you have actually like much smoother, and you can always use this kind of profile for like a complex system like a humanoid or even a complex manipulator and all, we can use this. That's why people try to use. For example, the legged locomotion, for example, the biped motion. So one foot to another footstep. So you need to make a cycloidal motion that would be very much beneficial. It starts from rest and end also at actually like standby. There is no further motion. So then the next step will start. That way we can do it. So now if I actually change this, for example, I am saying that it is actually like a run with only 2 seconds. So you can see like the variation would be very significant. But one thing you can clearly see that the acceleration is pure sinusoidal acceleration. So here I make it 0.1 as the step size. So that's why it is actually like look like very you can say segment basis. So for increasing that, you can actually like make it smooth. Okay. So now I just wanted to show that it is actually like sinusoidal profile. You can see like now it is smooth, right? So that is actually like I make it only for plotting what segment I want to give. So I take every 0.1 second, in the sense 100 millisecond, but in this case, so I have taken 10 milliseconds to show the smoothness. So here the acceleration is we call sinusoidal acceleration. Even some people call the cycloidal profile called sinusoidal acceleration curve. Okay. So this is what the cycloidal. So we'll see the final one on this particular lecture is what you call straight line interpolation with the parabolic blend. So you know straight line interpolation means starting to end we just make a straight line and the slope we will take and multiply, but that is non-smooth because the acceleration at infinite at initial and final, which is not possible in the real time, the actuator will not be substantially support that. So for that only we are doing the blendness. So what we are trying to blend, so we are taking the same straight line into 3 segment, the initial and final will add the parabolic segment. So that is what we are trying to do. So you can see that the TB is the parabolic blend, okay. So where that segment time. So now you can see that T0 to TB is the parabolic. So the parabolic can be written in this form. So then after that it is a straight line till so TF minus TB, then TF you can see where the T is start from actually like TF minus TB to TF. So there you will be using again the parabolic. So in that sense the profile is actually like much smoother and it is actually like faster to use. However, the algorithm is actually like much complicated. So you have to actually like bring this VB and AB in such a way that the profile will fulfill. So for that we are actually like bringing this consideration. So where this VB and AB we have to choose, accordingly the TB will come. However, while choosing, so you have to make sure that the VB squared by AB should be always less than or equal to 1. So if you take this, further consideration is actually like you can take that the capital or you can say TF should be take at least 3 times of TB. So then only you can make a blend. So these are all complex. However, what we can do, we can actually like take this particular consideration and we can make as a S of T. So then we can actually like multiply with your original x of 0. So why? Because this would be run for 0 to 1. So then we will actually like multiply whatever the segment you wanted. So that's why you can see like xf minus x0 multiply with s and s dot, everything is coming as this. In the sense we are multiplying that many times. So for that we are writing the code. So here we need to define VB AB. Similarly, the TB is defined based on the VB divided by AB, and we have actually like taken this. So here actually you can see again 5 seconds. So we are taking actually like first 1 second for parabolic, the next 3 second is linear, then final 1 second is for parabolic. That way we make a blend. So because we take a VB and AB are 1/4 each. So in that sense the TB is 1 second, right? So based on that we have written the code, whatever we have written in the you can say syntax, the same thing we have written. So now you can see x, v and a would be based on you can say AB and VB. So that we have actually like obtained. This is a parabolic, then straight line, another parabolic. So this way we have written, and we use the simple plotting function, but now the plotting function is modified because we have derived only s of t, but the s of t need to be modified as x of t. So we need to actually like multiply this particular value. So that's why we have modified this. So now we will actually go to the MATLAB and we can actually like see how that will work. So for that we are taking the parabolic blend. Okay. So now you can see that VB and AB we have taken as 1/4 each, and in that case you can actually like see this. So we are actually like taking into this consideration. So now I am actually like modifying the equation earlier we have written, that I modified into 3 segment, and then I am actually like plotting it. Okay. So in that sense what we can do, so if we run this, so you can actually like feel it what exactly happening. So you can see, right. So this is the constant acceleration stage and this is constant deceleration stage, where the velocity would be starting 0 to increase to maximum, then the constant deceleration maximum to 0 it comes. So in the middle segment you can see that it is a straight line where the velocity is constant. Okay. So like that we can actually like keep playing it. So now this will give much better aspect. So now you want to actually like increase to 2. Okay. I said that is 5 seconds, but I want to increase to 2. So what I am actually like trying to make it, this is 1/2. So now I am actually like keeping this way. So in that sense you can see the TB become 2. I'll just check. So I did not try. So I'll just check. So now you can see like it is actually like make it, but now the proposition is changed, right. So now you can see like it's supposed to end with 5, but the proposition has changed. So we have to actually like see here what we made. So this is actually like modify into some consideration of VB. So now in that case we have to actually like modify. Okay. So that's why I said this what you call parabolic blend is very difficult to make it, because you have 3 equations. Okay. Or you can say you have 4 equations and 3 unknowns, it is very difficult to fulfill. So that's what the consideration it is. So now if I actually like make it, this is the other way around. Okay. So now I actually like modify this into a slight consideration. So now you can actually like see that this is still 1, but the velocity and acceleration is modified. So now the acceleration and this one is modified. Now the position is actually like shifted according to that. Okay. So like that you can actually like make it. So even when you wanted to do it a constant acceleration and deceleration, then you can actually like assume that, you just assume that, so you are what you call this TF is still 5, but the TB is 2.5. So then you will actually get only 2 parabolic blend that make, so which we call constant acceleration and deceleration. So this we have seen already in the you can say lecture. So now this way we can actually like play it. So I already said this is actually like imposed with some additional constraint. So for example, I am actually like putting this into 3. So we can actually like see whether that is actually like following it. You can see. So it is actually like not exactly matching, because you can see if you modify, that step is actually like varying. So instead of that, if I actually like keep it this 1:1, so you will actually like see that this would be following it. Okay. So now you can see now, so what is the proposition it is making? So it is 1.3 or something. Accordingly you have to make a proposition. Earlier we have seen it is so 1/2 each. So in the sense it is actually like 0.5 and 0.5, which is equal to you call 1. So now it is actually like you can say 0.67 plus 0.67. So that way it is actually like added. Okay. So what I mean to say, so for example earlier case we have taken is 1/2 1/2, which gives, you can say, total addition is actually like 1, right. So but now here is actually like 1/3 and 1/3. Okay. So in that sense what would be the XF? So XF would be like 2/3. Okay. So that multiplication would come, or the other way around you can actually like make it. So you can say this particular proposition you would be adding it. Okay. So that way we can actually like see it. So in the sense we can actually like add that. Okay. So now we will actually like keep it this as it is. So that proposition you have to actually like multiply. So that's why the parabolic blend is not so common to most of us. So because that actually like you little trickier one. So now you can actually like feel it, this is actually like happening. Okay, so now I just make it this, so we can actually like see this will go to 4. Okay, so now if I actually like make it this is 1 by 4, so it will actually like remain what you call that aspect. You can see it is remaining 2 meter per second, or you can say 2 meter. So these all actually like what we want to say in a parabolic blend. So now whatever you are getting, this is actually like so the addition of this, so VB plus AB, whatever addition is coming, so that multiply with twice, so that much would be your proposition. So in that sense, so here whatever you are going to get, so that this x would be that many times. Okay, so now if I actually like say this, so if I actually like make it this is 1 by 2, okay, so then I can actually like see that this would be, so divide by something like, so 2. Okay, so if it is actually like 3, then it divide by, you can say 2 by 3, so it is actually like in the other way around, you have to multiply 3 by 2. Okay, so that kind of cases all will come. So that is what we wanted to see. So now I just run this and end this. Okay, so now you can actually like see it. So these all by experience only will come. So that's why most of the industrial manipulator, they go with you call cubic polynomial or cycloidal, or even you want to control the acceleration, they go for, you can say, the 5th order quintic one. Okay, so with that I am ending this particular lecture. So we will see in the next lecture how we can generate the you can say manipulator trajectory. So for that we will take a simple example of 2-hour serial manipulator, and we will see how the joint space and task space schemes can be generated and realized in the MATLAB. So with that, see you and thank you. Bye.